This short tutorial is about how to make our home more livable. Many of us have suffered in a hot house or a cold house, and now there are designs for passive houses.
The way that we build in this privileged society, it's a high level of manufacturing. It's really quite hard to achieve what we would call genuinely sustainable. That there's a cost environmentally and financially difficult to wear the cost of building at the moment. It's no longer about shelter, it's about capitalism. When you're starting with our housing stock that is not well designed, not well built for passive solar, what are you supposed to do about that? The system we have is not necessarily the one we have to have. In a lot of European countries, renters have much more security, that they have these very long leases that are really hard to break as a landlord, and it is worth upgrading the performance of your rental because you know it's going to pay for itself.
But what makes a home comfortable? What's the Goldilocks recipe? Traditional homes in cold climates are usually squat, and they're often rounded to reduce the effects of wind and for the ease of construction. And they have minimal airflow and high insulation. Whereas homes in the tropics are often elevated, that shades the area below. They are tall and narrow, have high ventilation, high airflow. The steep roof also helps to shed water. They have low insulation and low thermal mass. Homes in the deserts traditionally are squat. They have high thermal mass, often have a flat roof so you can sleep on it at night, and small windows to reduce the sun's heat rays. So what are the keys to comfort? The keys are that the building needs to be warm, not too hot, not too cold, dry, light, good amount of light to work with, clean air, and secure. Let's have a look at temperature. It's nice to be cool in summer and warm in winter. To be cool, we need to shade the area, insulate it from the sun's rays, and have air movement. That can be created by the shape of the building or by devices like fans. And we can use something called a heat sink, that is, a block of thermal mass to absorb some of the heat.
You might have a window facing the wrong way. That can actually be favourable at certain times of the year. So a northwest facing window is actually quite pleasant in winter, but it's just too hot in summer. And you can buy insulated shutters that sit on the outside of the building, and you just close that whole window up in summer. And I've got a French client at the moment, and that's exactly what they do in Europe. They've got all those shutters and they just open them up in winter, and then in summer they just shut right out all of this glass on the sunny side, and they don't quite shut it out. So they'll fold over these French doors and they'll leave them open just a little crack, like an inch or two, and it shades all the glass, but it lets a little bit of airflow in. So with passive solar, it's often the occupants who are active in modifying the building throughout the seasons.
So how do we create warmth? How do we make a space warm? We can use energy from nature, but actually our bodies create a lot of warmth. And so if you are cold right now, the fastest way to get warm is to insulate your body, put some more clothing on. We can reduce the amount of air movement because we know when air moves, it cools down. And we can insulate the building so the warmth is not lost. The buildings need to stay watertight, and by being watertight, we have more control over the temperature. So if you are sitting in a very, very hot building right now and you have enough water, you can hose or mist the roof. That's a quick way to cool the building. Open all the windows and doors and put fans on to get the hot air moving. In winter in particular, we don't want to have water in the building or even underneath the building. So if you suspect that water is flowing under the building, it can cause mold, but it can also cause the building to get cooler. So let's have a look at insulation. There are many creatures in this world that use insulation, like the bear in a cave, and the fur on its skin, and the sheep with its wool. But when we look at the elephant, it uses its ears to cool down. It fans those gigantic ears to cool its body. But if it was in the snow, then it would benefit from insulation on those ears because they would be very cold. The ears are like thermal bridges. They move the heat from the elephant's body out into the air. So if you have a doorway or a window that has wood, a wooden lintel right through from the inside to the outside, that is a thermal bridge. When we cover the thermal bridge, we're reducing the heat loss or the heat transfer from outside. Thermal mass is usually a bulky material like mud, boulders, or even water tanks. A brick floor or a wall can act as a thermal mass. In many ways, it's the opposite to insulation because insulation is usually light and airy, using the trapped air to block the transfer of heat. However, wood can act as a thermal mass, but it can also act as insulation. Some homes, especially underground homes and cave homes, don't need much thermal mass because the cave or the soil around it is the thermal mass. And we see evidence of ancient underground housing, as well as many modern underground houses use the constant temperature of the earth. Now, one of the most important aspects of building a design is its orientation, the way it greets the sun. Thousands of years ago, Socrates noticed that when the homes are facing the sun, the light can penetrate into the home. And if there's a portico on the front, that stops the hot summer sun from coming into the home. But in winter, the sun can still get through underneath the portico or the porch. So he suggested that we elevate this sunny side and lower the sunless side to block out winter winds. That's the basis of solar passive design. It allows the sun to come in winter but not in summer because it has shade control on the sunny side and not many windows, if any, on the sunless side. But it also has thermal mass on the floor to absorb some of the energy during the day and release it at night in winter. Here's a home that was designed by Frank Lloyd Wright. It used the same principles, but it incorporated a berm on the back of the home. In front was a large section of glass, and overhanging is the roof. It comes out sufficiently so it blocks the sun in summer. Earthships are very similar. Here I am in an earthship in Taos, New Mexico, United States, and it is in the middle of winter. You can see some snow on the ground. There was no heating for this house, and you can see the sun is coming through onto a small dividing wall, which is a thermal mass, dividing the area between the kitchen and the living room. And you can also see a little bit further to the right, and a little bit screened for privacy, I imagine, is a large thermal mass in the bathroom. The passive housing standard doesn't rely on sunlight, but you can have the same treatment on the sunny side. You can have your windows, but they tend to have triple or double glazing on all the windows because the whole passive house standard requires that it is super insulated. The thermal bridges are covered, and so there's very little chance of any exchange of energy, warmth from the inside to the out or vice versa.
The colder your climate, the more that passive housing suits. It's useful also in a warmer climate that's subject to heat waves. The passive house is about like really super heavy insulation and the ability to shut the building completely off the outside world and then really carefully regulate the airflow, the temperature movement across the wall. So we're probably going to need more and more houses that are resistant to heat waves. I like that it measures the actual built performance, because in Australia we've got this big gap between the theoretical performance and the stars that are awarded to a design compared to the actual built performance. And it is quite hard to measure whether the house really stands up, and Passive House is very clear on what the standards are and how you measure them.
There are a couple more things that make homes feel livable. Being secure includes being fire safe, and there is a standard for this. We need to determine if the building honestly meets the standard or make plans to escape. And chemical safety is a factor, especially if the homes are surrounded by pollution or have lead paint or have a long history of chemical use for pest control. In the building construction phase, we can choose to use physical barriers like a termite mesh instead of chemicals, but this is tricky to retrofit on established buildings. Homes are more livable when they provide other functions, such as harvesting water, generating electricity, supporting indoor production by having sufficient natural light. And some buildings have really good outdoor spaces where we can work. They provide windbreak, frost protection, some reflected light, some shade, and of course the runoff water. To design for the variation of the seasons and for climate change, use the angles of the sun to set up shade. Add thermal mass or phase change materials within the home. Add insulation, especially between the roof and the ceiling in that cavity. Block thermal bridges, such as window and door frames. Adjust the airflow. An increase in ventilation will be cooling, whereas when we block off rooms, divide the rooms, it makes them snug and warm. In summary, livable buildings are warm, they're not too hot and they're not too cold. They're dry, they have good natural light, they are safe and secure. And I hope this has given you lots of ideas on how to improve your home.